wait 1 minute, just in case, just to be on time. Okay, 9 o'clock. Good morning, everybody. My name is José Luis Perez Aparicio. This presentation I am going to show has been done in collaboration with a couple of former PhD students of mine, and is entitled Numerical Methods for Some Multi-Physics Problems. Multi-physics is just a fancy word that has been in fashion in the last 10, 15, 20 years at the most. And it means basically to work with several fields of the physics. In particular, we will be talking about mechanics, of course. Most of us come from the field of mechanics, but the idea is to couple this field mechanics with electricity, with magnetism, and with temperature. What is the motivation of that? Well, the motivation is very old. Many centuries ago, very close to here in ancient Greek, they liked it very much a stone. It's not really a stone, it's a resin called amber, coming from the Baltic Sea. It was because they some friction to this stone, and it polarizes. And that was very funny for the people, because they didn't fully understand what was going on. What was going on is that somehow this stone is a piezoelectric, what we call today a piezoelectric, of course. And we will try to develop all of these concepts. Of course, this is not a class on electromagnetism. Electromagnetism is a field by itself. Is huge. There are thousands or hundreds of thousands of people working on that field. What we are trying to explain is how these four fields I mentioned before interact, and especially with the idea of putting a formulation into finite elements, into numerical methods. I'm going to talk about finite elements, but once you have the governing equations, balance, constitutive, kinematics, what we call kinematics, etc., then you are able to put that into a finite element program. Once you have a finite element program, you can solve complicated problems. Okay, myself, Pablo Moreno and myself are coming from the Polytechnic University of Valencia. As Adnan said, Roberto Palma now is working at the University of Granada. Table of contents. Well, very quickly, related references. That's not very important now. Fundamentals of electromagnetism. Of course, if you want to put electromagnetism into finite elements, you have to understand what electromagnetism is. We don't understand electromagnetism as most electrical engineers or material science people do. Of course, they are the experts. It's not I don't mean that we are better than the others. Not at all. They are the experts, and they are the ones who are devoted to solve real electromagnetism problems. But we have a very particular view on electromagnetism, because the end, what we are after, is to analyze active materials. Active materials are materials in multi-physics that can couple two or more of these fields I mentioned. Why that? Well, because they have a lot of industrial, technological, scientific interest. We are completely surrounded of active materials. When you have a watch in your hand or in your wrist, and it makes a noise, it is a piezoelectric, the one which is making the sound. I am sitting right now in my hotel room by a refrigerator. This refrigerator is a small refrigerator, of course, doesn't make any noise. It is not based in the typical Carnot cycle, like the refrigerators in your home or the industrial refrigerators. They are based in thermoelectrics. Thermoelectrics that are interesting materials. I will talk about that at the end of the talk. And they have the ability to produce electricity from heat. That's an interesting concept. Most people or everybody in engineering knows that when you produce heat, you gain entropy. So somehow you degrade energy. Well, these materials are able to do just the contrary. From degraded energy, which is heat, they produce active energy, which is electricity. Coming back to the example of the refrigerator, from electricity, these materials are able to produce cooling without any moving part. That's important. Of course, thermoelasticity. If we are talking about thermal field, as I did one moment ago, you have to understand thermoelasticity. This is nothing new. Thermoelasticity has been going on for many, many years. In fact, since the beginning of the 19th century. Active materials themselves, numerical methods, perhaps this is the objective of the talk, numerical methods in multiphysics, then a few examples. Okay, these are the references. You don't need to write them down. You can take a look to them if you're interested later. We have been producing papers from that for many years, for something like 25 years. And we started, I did my PhD in computational mechanics at Stanford many years ago, I am afraid. Many years ago, it's something like 30 years ago. Since at that university at the time, there was a very, very strong tradition on theoretical elasticity. So I took a fair amount of courses on theoretical elasticity. On the other hand, computational mechanics was starting at the time, well, was getting ripe at the time. And for computational mechanics, you need advanced elasticity. So I also had to take, or let's say, continuum mechanics in the modern sense. So I also had to take many courses on continuum mechanics. In a visit I had to a university in Philadelphia, Drexel, I made contact with another professor who was also from Stanford, who was working on piezoelectrics. At the time, that was but it was very new. And this professor, Horacio Sosa, was working on the theory of elasticity related with piezoelectrics, of course. With piezo in Greek means something like movement or mechanics or something like that. He was working on the theory and I was working on the numerical part. So that was the way, well, this is the way things start when you do research or in many aspects of life. I only put here a few examples. Professor Taylor from the University of California at Berkeley has been working with us, and it has been a big help because he's the author of the finite element code we are using. About that, we will talk later. And then there is this brilliant student, Pablo Moreno, who now is also a professor, and he did he finished only 1 year ago, 1 year and a half. He did his thesis with Adnan Ibrahimbegovic, and I was the co-advisor. In any case, I insist, don't take a look to these papers now, because this is something to be done later if you are interested. First of all, very brief review to mechanics. You have seen a little bit of you have seen a lot of mechanics and computational mechanics in this course already. You have a body, and this body gets deformed. Why? Well, because of some loads or because of some temperature from an external action, let's say. You start at t equal to 0, initial configuration, and you finish at t equal to t deformed configuration. And you have to measure that. How do you measure that? Well, a certain point, p sub 0 is going to move to p. Not much emphasis on that, but this is something that is for us in the 21st century looks very obvious, but that was not obvious at all. There was one of the most brilliant scientists of the history, Galileo, tried to solve this problem. He was really interested in astronomy, but he got into trouble by studying the stars, and he decided to do something more neutral, which was a beam. He started to study beams, and he didn't understand the problem. He didn't understand the idea that to study a solid, you need to look to the deformation. And probably the reason is obvious. They were seeing beams at their houses, they were seeing beams at the bridges, etc. But they didn't, beams, even if they are made out of wood, don't deform too much. Well, that's very obvious to anybody. Yeah, and if the beams are made out of steel, well, they don't deform. To the simple eye, they don't deform almost anything. But that's the key. That's the key. That's the key. And it took until 1820 or something like that with Cauchy and the people, Bernoulli and the people of his generation to understand that. Everything in mechanics is based on this deformation, even if it's 0.1 millimeter. Everything is based on that. In any case, we continue. Strain measure, that's what I mentioned before. When something moves, when one point in a solid moves, then you can measure how much it has moved with respect to the previous configuration. And this is what we call a strain. Okay. A strain is a complicated thing. It's a very complicated thing. In fact, the difficulty of mechanics comes from a strain. When you want to do simple calculations, it's not complicated. For instance, if your material is linear elastic and doesn't plastify and is homogeneous, you don't have composites, etc., the idea is very simple. You have a bar, you pull it, and the increment of length divided by the initial length, that's the strain. But when you go to large deformation, when you go to plasticity, etc., it really gets complicated. In this talk and in the results I'm going to show you, the strain is the simplest one you can imagine. It's linear elastic. It's linear. And the material will be elastic. We have done some work in materials that are not elastic or plastic, but it will be not part of this presentation. Okay, so basically you have a deformation, and this is represented by this nabla, cross product of nabla. Don't make confused by the notation. The notation in this class gets very heavy, but I will try to emphasize the concept. We don't want to make you in 1 hour and a half experts in this field. We want to understand you the basics, because this is the most important part. Once you understand the basics, there is left a lot of work on mathematics and on physics, but is the first step, which is the most important. You can divide the deformation of the movement into the two parts, the symmetric part and the skew symmetric part. You can do that for any tensor, and deformation is a tensor. Again, everybody is familiar with the notion of a force, because it's very easy to represent a force. What is a force? Well, that's very natural for us today. It was not very natural a few centuries ago. A force can be even represented by an arrow, and that's very easy to draw. And we engineers like to draw things. A tensor cannot be drawn easily. Well, you can use the more tensor, but it gets complicated. In any case, the idea is the formation is a tensor, and it can be divided into a symmetric part and a skew-symmetric part. We are going to use only the symmetric part, which applies under some hypotheses, of course. The most common, but not all of them. Tomorrow, I will give a talk. I will give a distinguished lecture in we start exploring the skew-symmetric part of things, because they are necessary when you go to advanced ideas, like when you miniaturize devices. Now there is a big fashion on nanomechanics. And when you go to nanomechanics, when you go to complicated applications, is when you really have to start using the whole mathematical apparatus. A symmetric part of you. Epsilon is a tensor, has 6 components in general. We are going to restrict ourselves to only 3 components: epsilon 1, epsilon 2, and epsilon 6. Epsilon 6 is the famous shear. Okay. Again, compared with the thermal field, for instance, all of these mathematical involvements are more complicated. But well, anyway, it's the way it is. So what do we do? What do we do in a body? In a body, we can draw a little mark, which is this differential view. And when you apply the deformation operator, you will finish that this mark has elongated or shrink, and it also has rotate. That's very easy to understand, no? Well, the rotation is related with the skew part of you, and the elongation is related with the symmetric part of you. Anyway, something to remember is that we work with, in 2D, that means that we work with epsilon 1, epsilon 2, epsilon 6. That's all. Next thing, the momentum balance. Everything has to be in equilibrium. And this is what the equations of momentum tells you. I am not sure. Here it is. Yeah. Oh, no, I cannot do that. Can you see the whole screen? Adnan, can you see the whole screen, or is it cut by the Zoom window? Anybody there? Anybody there can tell me something? Hello.
Yes, Professor. What do you mean?
If you can see the whole screen, or it is blocked by this window.
Only one slide. Only we can see only the slide.
But can you see the complete slide?
Yeah, complete slide.
Okay, good. Then good. Then it is good. Okay, equilibrium. Equilibrium, well, again, is a concept that everybody has. A structure has to be in equilibrium. In mechanical equilibrium, a structure usually is not made out of active materials, it's made out of passive materials, like steel, for instance. Well, you build the structure, you load the structure, it deforms slightly, and then it rests in equilibrium. That's another big concept that was developed many years after the idea of deformation. In fact, it was developed at the end of the 19th century. You can also find the solution of how your structure works by minimizing its energy. This is the very famous principle of minimum energy, principle of virtual work, all of these concepts. And modern numerical methods like finite elements or boundary elements are in part based on this concept, minimization of energy. The first step is the momentum. there are two momentums. There are the linear momentum, which is the one you see here, and the angular momentum. The angular momentum obviously is related with this skew part, which is a rotation, angular rotation. Okay. Tomorrow, as I mentioned in one of the lectures, of the first lectures, I will talk of applications in which you really need to look at the rotations. For now on, no. For now on, only linear momentum. Well, it tells you that the momentum, the variation of the total momentum is equal to the external forces, etc. Then you get this equation here, which is boxed. Okay, I'm not sure. Well, anyway, if you cannot see the right part of the slide, it's a problem. But anyway, what does it say? It says this is the Newton's law. This is Newton's law, but obviously Newton didn't. They were not invented at the time, or not very well invented at the time. But it says, it tells you the other forces. That's all. That's all what the second Newton's law says. Inertial forces, which is the density multiplied by the acceleration, equal to the other forces. And here is the concept, the brilliant concept from the beginning of the 18th century, as I mentioned. The external forces are F. It can be gravity, it can be centrifugal forces, it can be whatever. And the internal forces are the gradient of sigma. Before I have talked about the tensor deformation, now I introduce the other tensor, which is a stress tensor. Okay, and it has a supra C. This is Cauchy, which is the guy who developed this theory, sigma Cauchy. This is the usual one. This is the one you learn when you study elasticity or strength of materials or structures. It's the common one. It's a very easy, or at least compared to the others, tensor to use because it's symmetric. Cauchy tensor is symmetric. This T, it means only, it's notation, it means transpose. It's just to have all of the tensorial notation coherent. Transpose. This T is not temperature. Be careful. So we have this Newton law in the form of, in the tensorial form. This is the equilibrium or momentum balance. This thing here is the Levi-Civita symbol. It only means that if you apply the Levi-Civita symbol to a symmetric tensor, you get 0. That's all. And again, we will use only, we will apply it for only 2D, which is in the first direction, in the second direction. The third direction doesn't count, but in the plane of the first and the second direction, you still have the shear. Okay, that's all for mechanics. We really don't need much more than that. An interesting application or an interesting issue is that sometimes you are working in 2D, but you still need to use all of them. Why? Because you add the rotations. And again, this is what I will talk, this is the main idea of what I will talk about tomorrow. Okay, let's go to electricity. Very simple concepts in electricity. This is really like electrostatics. There is something that is important, which is called polarization. And this is for us who are coming from the field of mechanics of solids or mechanics of fluids. This is new. Polarization. Well, you know that all atoms have electrons and a nucleus and everything. In the mesoscale, we don't consider the atoms, or in the macro scale. In the macro scale, we consider that inside a molecule, there is some part which is charged negative and another one which is charged positive. that creates an electric field, okay, which we call E. So the polarization is the average of all of these dipoles, okay? The unit of a negative and a positive charge we call dipoles. Is not atom level, it's more like a molecule level, but well, it's another way of looking at the electricity. The polarization only conductor materials don't polarize. Okay, conductor materials don't polarize. This only applies to dielectrics. And they are very important. Dielectrics are very important. Piezoelectrics, for instance, or the amber stone I mentioned before, are dielectrics. They don't permit a flow of electrons. Okay. Okay. So the relationship between polarization and electric field is these two magnitudes. The Xi is the electric susceptibility, and the epsilon is the permittivity. Okay, permittivity or permeability, I never remember. Permittivity, okay? Okay, now, so we have two new concepts. The concepts I am going to use in what follows are in red. Another magnitude we need is the electric induction, which is something, is some material parameter, in this case epsilon, multiplied by the electric field. Okay, epsilon sub 0 is the magnitude related with vacuum. Epsilon sub s is the magnitude related with solid. Okay, for conductors you wouldn't have this p here. Then you will retain epsilon 0 multiplied by e. There is an interesting concept here. Look, D is taking the role of sigma. Of course, right now we are in electricity, but from the mathematical point of view, D takes the role of sigma, of stresses, and E takes the role of strain. Okay, and that's very useful. If you take a look to electricity or to any field in physics, and there are many, in this way is when you can apply the finite, when you can finish with a finite element method algorithm, and you can write it in Fortran or any computer language, and you finish with a computer program. Okay, this is what we call in mechanics constitutive, because you have some. This is not a tensor anymore. This is a vector. Okay, it has three components, or two components if you work in 2D. One vector equal to another vector multiplied by a material parameter, which in the case of a solid dielectric will be this epsilon s. Okay. Well, if you take a look to that in this way, you will be able to construct the finite element. Okay. As I write here, D and B have the same role as sigma Cauchy, and P and M has the same role as epsilon. I am advancing myself. B, we haven't defined B, but B is exactly the same as D, but in the magnetic field. It will come in a moment. The orientation is very important. I will show a picture in a moment. It is not the same that all of these dipoles are vertical, that they are horizontal, or that they have random directions. The implications in the electric field are completely dominant. Not only in the electric field, the fact that these dipoles are in some direction or other direction even implies that the material is not isotropic anymore. And that's, well, here we are seeing a coupling between electricity and mechanics. And well, if a material is not isotropic, you know that its study is more complicated, because you start having material constants, not only the Young's modulus. Okay, Xi, as I mentioned before, is the electric susceptibility. Okay, next thing. If a material is nonpolar, that's it. If a material is nonpolar, polarization is 0. If it's polar, then P is different than 0. Notice that P doesn't have a direct counterpart in mechanics. I repeat the idea because it is very, very important. D is in electricity is equivalent to stresses, E is equivalent to strains, and P doesn't have much, as far as I know, a counterpart in mechanics. Okay, there are many types of, well, there are more types of materials under the point of view of polarization, electrets, ferroelectrics, etc. Semi-ferroelectrics, well, plenty of things. The people who really study that in deep detail are the chemists and especially the material science people. But for us, all of these issues that for them are very important reduce to a magnitude, which is P, a vector. Of course, a P is a function of space. You don't have the same P in a part of a body that in the other. By the way, I am throwing to you a lot of ideas, and probably you will miss some. Please interrupt me instead of waiting at the end. Interrupt me, because if not, everything is very boring. And we have a fair amount of experience now with online classes. Most classes or all classes last academic year or even this academic year have been online, and it is a fact that people tend to start thinking in other things. That's natural. It happens to me too when I listen to a talk. So if you have something to contribute or you have a question, please tell me. Okay, we have taken a look to this dipole, electric dipole. There is something similar which doesn't have much physics behind. That has a lot of physics behind, because as I mentioned before, well, you have electrons going around and going around a nucleus, an atom nucleus, and everybody knows, or almost everybody knows, that electricity is the movement of these electrons. Okay, we can think about something very similar in the magnetic field. You don't have electric dipoles, but we have what we call magnetic dipoles. They are not two charges. They are something that goes around. We can think about that. If you have something that goes around, then you have a rotation. It's not the same rotation as the mechanical one at all. But if you have a rotation, you will have a related normal to this rotation. Okay, well, so we define two new things. H, which is the magnetic field, Teslas, unit Teslas, and you have B, which is the magnetic induction or magnetic flux. Again, B, role of sigmas, of stresses in mechanics. H plays the role of strains in mechanics. And we have very similar. We have a permittivity of space of the vacuum or of the solid. Well, it really depends. And we have relay. I kind of mentioned before, everything which is constitutive is a property of the material. You don't have the same magnetic permittivity for iron that for plastic, let's say. It's completely different. And it's something that has to be measured. In engineering or in science, mathematical models are there to be used, but there is a hard work to measure properties. which we engineers usually don't do, or do only in part. We will see about these properties. When you start working with many fields, you finish with a huge amount of properties. And some of them are very well characterized and some of them not much. Okay, so if you apply a magnetic free field H to a material that has magnetic dipoles randomly oriented, you will not get magnetization, because somehow all of these vectors. But if you finish with a material that all the dipoles are oriented in the same direction, is when you finish with a magnetization, and that has a lot of applications, a lot of sophisticated applications, by the way. Military, industrial, all types of things. Active materials. We will see that this is what active materials. If the material science people are able to produce this type of materials with dipoles completely oriented, then you finish with a material with interesting properties. Okay. Well, again, left they are diamagnetic, and right you can find many types: paramagnetic, ferromagnetic, anti-ferromagnetic, etc. It's not the object of this talk really to divide the materials. We will take a look either in the class today or in my lecture or in my talk tomorrow. We will see some real materials. Okay, semiconductors. Well, conductors are materials that allow electrons to go through, and there is this conduction band, etc. And then is when you divide the materials in conductor, dielectrics, isolators. Dielectrics are isolators, or semiconductors. Semiconductors are important materials, of course, no? In electronics. In electronics, all the materials, well, the important materials, the most important materials are semiconductors. But the materials I mentioned before, thermoelectrics, also are semiconductors. So that has to be taken into account. Many people contribute to electromagnetism, from Fourier, Seebeck, Ohm. You probably have heard these names in physics classes. That was, notice that some people are very ancient. No? This Linné, who also did a contributions in elasticity, died before the 19th century. And then you have some other people who are newer generation. This is the brilliant generation in physics: Hall, Nernst, etc. The generation of Einstein, which is when the physics make a huge jump. Okay. Well, our equations are based on people like Fourier or people like Ohm. Our basic equations are based on 18th century people. But when you want to study advanced applications, the nanomechanics I mentioned before, the actuators or sensors I also mentioned, then you have to go to the next generation, well, to a few more generations, like Hall, Nernst, Debye, all of these people who work at the beginning of the 20th century. There is something interesting that is say that the 19th century was the century of the engineering. It was when railroads were developed, even when the beginning of aeronautics, although the first flight was in 1903 or so, 1904. The 20th century has been the century of physicists, and they are these people, Hall, Nernst, Einstein, Oppenheimer, etc. And the 21st century is the century, or is going to be the century of biology. Okay, so we engineers are kind of old-fashioned, but still necessary. Okay, next thing, electromagnetism is controlled, or what describes electromagnetism are the famous Maxwell equations. And we have to study them because they are the equations we are going to put into finite elements. The study of static and moving electric charges. That means that we have to work with fields. In this sense, we have an advantage over mechanics. Mechanics is complicated because we have to work with tensors. There is no way to avoid that. Tensors. And tensors, well, with tensors is when you get these shears I mentioned before. Electromagnetism only has fields. In this sense, it's an advantage. These are the Maxwell equations. By the way, Maxwell didn't develop all of these equations. They are called Maxwell equations in the, well, Maxwell put together all these equations, something that the field of physics is very well appreciated. It is relatively easily to produce the equation like Ohm's law, for instance. Well, I don't mean it's easy, it's relatively easy. What is difficult is to put everything together, okay? And this is what Einstein tried to do, and more or less he did. The physicists have been working in an unified theory of gravitational and all of these things for many years and still haven't done it. Okay, Maxwell was able to do that with electromagnetism. Okay, so here we have laws that look complicated, but they are not that complicated. They're linear. They are linear, and that's good. When you work with differential equations, if they are linear, you have a big advantage to solve them. Okay, but they are four laws, and they have something which is rotationals. Everything which is magnetism is rotational, rotates. It's not that the solid rotates, it's that the field rotates, okay? And for instance, there is this law here. We'll see that in a moment. Here I define formally all of the magnitudes I have been presenting. E is the electric field, you see it. D, the electric displacement. H is the magnetic field. B, the magnetic flux or magnetic displacement. You have some additional things like J is the free electric flux, is the flux, that's all. No? And rho is the free charge density. In some materials, you have some things, in some other materials, you don't. As we will see in a moment, conductors have J, have movement of electrons, but dielectrics don't. Dielectrics don't allow the electrons to move freely. They allow the electrons to move in another way. Dielectrics have rho. For instance, static electricity is called. Conductors don't have rho, etc., etc., etc. Okay. These equations have names. The first one is Faraday's law. Second one is Ampere's. Some of them were really created with Faraday, with the name related. Some others were not. Well, that's not relevant for our objective, which is finite elements, but it's interesting to know. Electric Gauss law, magnetic Gauss law, and this is equilibrium. That tells you that the flux is continuous. The flux of electrons is continuous. This has a lot of physics behind, and we don't have time to go through. But for instance, this one here, notice that the divergence of B is equal to 0. That has implications. That, for instance, implies that the magnetic field lines have to close. It's not like mechanics, in which you have a force that doesn't have to close. You have a force, you pull something, and well, it somehow closes because you have action-reaction, but in the plane or in the volume doesn't close. It also implies that you cannot have monopoles. You cannot have magnetic charges. They don't exist. In some mathematical models, they include magnetic charges, but they don't have physics behind. On the other hand, in electricity, you can have charges. Electric charges, everybody knows what electric charge is. It somehow is an electron, okay? Anyway, these are the equations, these are mathematics, but they have physics behind. If you understand the physics, you have a little bit of advantage. Well, they are dynamic. You see that that have derivatives with respect to time. It's obvious, no? And they have cross products. Well, you can get rid of these two equations easily, and we will see in a moment how. And you will finish with these two. But these two are easy. Well, I mean, easy in the concept of numerical methods. If I go back to the, if I go back, and I have to go back a fair amount. Here it is. Here we have a divergence also. So in mechanics, we already have a divergence of sigma. In the Maxwell equations, we have a divergence of what I told you that plays the role of sigma, which is D, the electric induction, and B, the magnetic flux. So I advance a little bit the final results. We are going to treat into finite elements in the same way mechanics, than electricity, than magnetics. Okay. Electrical engineers do finite elements very, very different from people coming from fluid and solids. They like to use integral equations. Well, you know that any differential equation, or almost any, as far as I know, any differential equations can be converted into an integral equations. In fact, in finite elements is what we do. But anyway, this is just to show that in other fields they do things differently. Magnetic and electricity also have the rules. For instance, the electric induction must be continuous in the normal of two different mediums. That's important. While the electric field is continuous in the tangential direction. Well, these things we will not apply, but are some things that if you work with these issues, you have to know. Here we go. Here we go to the important things that are going to put us into finite elements very quickly. If you neglect this term, and when can you do that? Well, when the frequency is low. Okay. If you are working in telecommunications, you cannot do that because you work with thousands of hertz or thousands of millions of hertz. Okay. For signals, for theory of signals, you cannot do that. But for applications, for industrial applications of the sensors and actuators types, you can do that. You usually work only with hundreds of hertz. Then you can neglect this term and this other term. Then the Maxwell equations reduce a lot and they became very, very easy to work with. If you can neglect this variation with respect to time, and is what notice that this cross product is equal to 0. What does that mean? When you apply, here we go. When the vectorial product of I say cross product and it's probably not right. When the vectorial product is equal to 0, that means that this vector is coming from a potential, and this one is very common. It says that the electric field is the variation of voltage, nabla of the voltage, V, with a minus sign that has some implications, but for now we believe it. Okay, so well, that means that if we choose the voltage to be the gradient if we choose the electric field to be the gradient of a magnitude called voltage, then the first equation, the Faraday's Maxwell equation, is already fulfilled. It's automatic. So by using this compatibility equation, this is called compatibility. In mechanics, we call kinematics because it's related with movement. In electricity, it cannot be called kinematics because nothing moves here. And if we choose the magnetic field to be the gradient of something that is not as common as the electric voltage and is called magnetic potential, then the second equation, which is amperes, is automatic. We don't have to use it. Okay, so by using these compatibility equations, the first two equations are automatic. This is called electromagnetostatics. It's not really that the electricity has to be continuous. No. It can be alternate, but it has to have low frequency. Okay, so two Maxwell equations out by using that. There are more ways of doing these things. For instance, H can be a vector potential. And then the formulation gets more complicated. It can be done, It can be done. And in fact, we published a paper studying magnetics with finite elements. I think it was 2012, if I remember well, 2011, something like that. And this paper stayed like 7-8 years without absolutely any reference, or only 2 or 3. Then the use of vector potentials, which would be, instead of having nabla of a scalar, have nabla of a vector, then everybody got interested. And now this paper has like 80 references. So you never know. When you publish something, you never know if it's going to be good, if it's going to be bad or not. Well, you can imagine, but there are surprises. Okay. Then, well, you finish with a much simpler, formulation. Let's go to the balance. We already have seen a balance of electricity, which is here. Okay, that's electric charge balance, but this is not balance of what we want, which is balance of the electric field or the etc. In electromagnetism, you get this equation here, and that's important. This is one of the main ideas of this talk, and it's not very well known and it's not very well understood yet. The theoretical physicists are still working on that very heavily. By the way, physicists lost interest in electromagnetism at the beginning of the 20th century. Why? Because there were things that were much more important, like nuclear physics, like quantum mechanics, like statistical physics, and so on. But in the 90s, 1990, they returned to electromagnetism due to the industrial interest of nanotechnology. They needed of electronic circuits, of laser beams, etc., etc., etc. So electromagnetism is again a very active field in the physics because of the industrial applications, of course. Okay, what do we have? What do we have? The electromagnetic balance. We have again a derivative. We have a derivative with respect to time of D cross B. This is a coupling already. You see it. D is electric, B is magnetic. It's obvious. And we again neglect that for low frequency, which is equal to something which is, look, that looks exactly the same as mechanics. It's nabla of a tensor, of a sigma, of a stress, plus minus a force. That's exactly the same as mechanics. But we don't have the Cauchy tensor, the Cauchy stress tensor. By the way, stress is a concept I didn't mention. I realize it now. Stress is a pressure. Okay, it's force divided by area. That's all it is. When we say stress, we can think about pressure. It's more complicated than pressure, but anyway, it's one way of understanding. And a force is just a force. Okay. Oh, that's good. That's good, because we have a form exactly the same as that of mechanics. Since we know how to put mechanics into finite elements, and that was done in the 1960s, many years ago, and we have studied that, etc. We have an opportunity to put electromagnetism into finite elements with this expression. Of course, sigma, this is EM, means electromechanics. Sigma is not anymore the Cauchy tensor. It's not pressure. It's not force divided by area. It's this expression here, which is called the famous Maxwell tensor. Okay. It seems that Maxwell only developed this part. This part is symmetric, but this other part is not symmetric. It's nothing. It's not even anti-symmetric. Okay. It seems that Maxwell developed that, and some other researchers developed the rest. This is the symmetric part of the tensor. And well, it's good for vacuum, but it's not good for solids. It's not good for dielectrics. Well, we have an attractive expression, as I mentioned, but we have a tensor which is difficult to manage because it's non-symmetric, and non-symmetric tensors are not easy. Okay. Besides that, the Cauchy tensor can be derived from a potential. Like I'll mention what a potential is. It's not an electric potential. It's not voltage. It's something like the function of Helmholtz or one of those. To make it simpler, this sigma EM, the Maxwell tensor, is mathematically more difficult to manage. And then you have some forces, newtons. Of course, they are not expressing newtons, but they are expressing coulombs and amperes and so on. But they have relation. They can be converted to newtons. So here we have these parts: the Lorentz forces and the ponderomotive forces. And you see that well, we start having a lot of terms. Okay. Trick. There is a trick. There is a trick here. Oh, by the way, many people say that the Maxwell tensor is equivalent to the Lorentz forces, and it is true. It's true. Take a look. For low frequency, for sure, it's true, because you get that this thing is equal to 0. That means that the divergence of the Maxwell tensor is equal to the electromagnetic forces. But there are more things here. There are more things here. There are all of these ponderomotive forces. Notice that this is a cross product multiplied by another vector. It's a scalar, as a matter of fact, as you can see. It's a scalar. Yes. No. It's a vector. It's a vector. Excuse me, because that's going to finish being a tensor. We haven't worked much with the ponderomotive forces, because they apply only to very, very special occasions. We are almost getting into the quantum mechanics field. This is not yet quantum mechanics, but this is the beginning of quantum mechanics. And quantum mechanics gets complicated. It's much more complicated than classical mechanics. What do we do with these things? Well, we are going to do something interesting in a moment. We will see that in a moment. I can advance what the result is going to be. We get rid of this one here, and since we have nabla of the sigma Maxwell, we will add the sigma Maxwell to the sigma Cauchy, and then is when we finish with a very compact formulation, and then is when we couple mechanics and electromagnetism in a mathematically very convenient way. Okay. So forget the electromagnetic forces because we are not going to use them. And remember the Maxwell tensor because we are going to use it. Some people use the forces. The forces are also attractive because you know that, probably you know, or you have an idea that in finite elements or in any numerical method or in any analytical method, if you have studied strength of materials, point forces are very easy to manage. So some people use the forces, and there is nothing wrong with that, as long as you get good results. Okay, so Maxwell tensor does not derive from any potential. For instance, the Helmholtz functional. When you work in computational mechanics, you want to have this type of formulations. It is very convenient. It is very convenient to have everything from a potential. The rest of the formulation does. The two Maxwell equations left can be put into a functional, the D, capital D, the capital V, etc. Okay, this is the equation of balance, but from thermodynamics. We go into thermodynamics now. We have to have thermodynamics. First, because we are interested in the thermal field. And second, because one of the important issues when you study any process is how much energy you are dissipating. That's extremely important, of course. No? You have devices that get hot. You want to analyze, and eventually, if they get very hot, they break down. Okay, well, you want to analyze that. Besides that, you have non-linearity of constitutive equations. For instance, in magnetics, the only way of doing that is taking a look to thermodynamics. If the process is conservative, you imagine that the entropy is, the variation of entropy is zero. Then you get with the principle of minimal potential energy, we will go to that, that says that the increment of internal energy is equal to the increment or decrement of external forces. And we are going to define something important, intensive variables. Look, again, here we have in a table what I have been saying all the time. Stresses, sigma de Cauchy for now, the mechanical one, the electric field and the magnetic field. They are all intensive variables. We will see what intensive and extensive means. And what are the extensive? Epsilon, P, and M. Notice that they are related by material properties. Sigma is related with epsilon, with the Young's modulus, for instance. Well, in general, with the stiffness coefficient matrix. The electric field is related with polarization, with the permittivity, and the magnetic field is related to magnetization with the permeability. Okay. Here we have differential of internal energy as a function of extensive variables. It has to be done like that. Okay. And as I mentioned, the internal energy has to, the increment or decrement of the internal energy has to be equal to that of the external forces. And here we have the expressions. Okay. Once you have defined all of these things is when you can create your functional. And once you have the functional, then you can create a finite element formulation. Okay, well, what is the energy in the mechanical field? Well, it's the sigma multiplied by epsilon. Okay, this is all notation. This is the multiplication of two tensors. That's all it is. And again, this thing is the multiplication of two vectors. So the internal energy is going to be the extensive variable multiplied by the internal variable. We don't want the formulation like that. We want to go. We want to have some type of inverse, and this is what is called the Legendre transformation. We want our functional as a function of the strain, yes, but we don't want the functional as a function of P. We want the functional as a function of E. Why? We will see that in a moment. Because this is the way that the finite elements based on the displacement formulation are made. Then you have to start doing some mathematical changes, which is this thing here. As a matter of fact, it's a change of variable, but in the tensor notation, it's a bit more complicated. In matrix form, you finish with this thing here. Okay, you have to rearrange rows and columns so that E goes to the left and H goes to the left, and P and M goes to the right. Okay, notice that now you already are, by defining this functional, you are coupling the fields. You already have done that. Somehow with the Maxwell tensor, we had some coupling, but now we are doing that at the constitutive level, okay? Don't try to understand all of the terms, it's too complicated. Yes, try to focus on the concept. Notice that sigma, the stress, the mechanical stress, now is equal to something, a derivative of something, which is going to be the stiffness, by the way, multiplied by epsilon, which is the strain, and that's the mechanics, the everyday mechanics, but also some constitutive coefficients multiplied by the electric field or by the polarization, and also another constitutive magnitudes multiplied by the magnetic field. Okay, so here is the coupling at the constitutive level, the most important. Okay, here we have for dielectrics. This is only for dielectrics. In a moment, we will go to the differences between dielectrics and conductors. Oh, oof, lots of couplings, eh? Sigma is equal to C, the stiffness matrix, multiplied by epsilon, but another multiplied by the electric field, another which multiplied by H, and the thermal expansion coefficient. This is thermoelasticity. That's probably more known to you. And the electric induction, well, it is something which is epsilon supra V, which means the permittivity multiplied by the electric field that we have seen from the beginning, and also multiplied by another 3 couplings. So here you have a huge amount of material properties. This one here for this one here for an isotropic material only has 2, which is the Young's moduli and the Poisson coefficient. But the coupled materials tend to be transversely isotropic, and you finish with 5 or 6 properties that need to be measured. For some materials you have them, for some other materials you don't. Here you have couplings, lots of couplings, and all of these are things that need to be measure. From mechanics is the displacements. That came in the first transparency. I am getting a message saying that the connection is not very good. If you don't leave me, you don't see presentation, please, can I see the Simona, for instance? Are you there, Simona? Hello, Simona. Oh, maybe nobody can hear me. Samir, are you there? Well, okay. I will assume that you are there. Adnan, are you there?
What do you need, Professor?
Hello? I can hear somebody.
Yes, I'm here.
Who are you?
Yeah, my name is Oui, like we in French.
Okay, okay. The question was, do you get any cut in my talk, or can you hear well?
Actually, your slide, I can see a full slide of number 20.
But the question was about, can you hear me well, which is the important thing.
Sometimes the connection is really weak.
That means that you don't understand me, or
No, I can understand you.
good,
But
good.
sometimes the internet connection is not really good one.
Yeah, and can you see the screen well?
Yes, the screen is always well, but
Okay, good.
only the hearing. Yeah.
Okay, let's keep going. Degrees of freedom. UT, that's the electric degree of freedom is the voltage, and the magnetic degree of freedom is the potential, the magnetic potential. Primarily epsilon dB, we have seen that for 1 hour now, and interesting, the entropy degree is not a degree of freedom, so we don't need to calculate it if we don't want to. Okay, the things that in finite element displacement base are these things up here: 3, 4, 5, 6, and the dual variable is sigma total, which is the summation of the Cauchy and the Maxwell tensors, delta t, which somehow is the flux, E and H. See, all of these things are what we have been talking about. C, elastic material tensor, stiffness. Epsilon supra V, permittivity, mu, permeability. Notice that they are not a number anymore. They are in boldface. Okay, so that means that they are tensors. In general, these are diagonal tensors. But of course, you can have a thermal conductivity, different thermal conductivity in different directions. If your material is isotropic in the thermal field, well, then you have 3 numbers in the diagonal of a 3 by 3 matrix. Okay, so this is a huge matrix, because that one will have 3 components. This sigma will have 3 or 6 components. That one will have 2 or 3 components, which is the thermal flux. Okay. Well, almost no material needs all of them. That's the good news. Okay, there is maybe there is a material, but we have never solved this problem. Maybe there is a material that is mechanical and has electromagnetism, and on top of that gets hot or gets cool. Okay. Well, if that's the case, you will have to consider all the constitution. Electromagnetic, and then is you have the counts. Electromagnetic, piezoelectric. Here we go with the piezoelectric. Here we go with the electric, magnetic. All of these, piezoelectric are materials that have interest. As I mentioned, sigma total is equal to sigma Cauchy and sigma electromagnetism before. What you have, because if you remember, the electromagnetic forces are forces like any other, and they can be, and their units can be newtons. Well, so what do you do? You substitute that F supra EM, and let's go back. You substitute this one for plus divergence of sigma EM. Okay, and the divergence is an operator that is distributive, and then you finish with this very simple expression. Okay, well, the only problem is that you have to calculate the Maxwell tensor. Then you have the third Maxwell law, you have the fourth Maxwell law, and you have the equation of the thermal equation, which is Fourier's law. It's Fourier's law. Fourier is that one here. It says that the divergence of the thermal flux is equal to the thermal inertia. But if you do the complete formulation, you finish with new terms that are called Biot terms. Biot is one of these physicists I mentioned from the beginning of the 20th century. This one is very simple. This one is thermoelasticity, and this one was not invented by Biot, was invented by Duhamel, not at the beginning of the 20th century, but at the beginning of the 19th century. Thermoelasticity, a classical field. Then you get new terms. Which is this pyroelectric multiplied by the variation of E and the variation of H. What are these terms? Well, these terms are heat. This is the equation of heat. It's clear, right? This is the heat produced by mechanical vibration, electric vibration, and magnetic vibration, or variation through the time, if you want to. It is true that we have neglected derivatives of D and derivatives of B before, but well, maybe the derivative of D is negligible, but not the derivative of E. You only apply these terms when you work with very sophisticated applications, okay? And when do these sophisticated applications appear? Well, I mentioned one case, nanotechnology. When you have your devices that are extremely small, then is when you need to apply that. Since we are with dielectrics, we don't have electric flux, but we have thermal flux, and this is the Fourier law. Okay, for conductors, or let's say semiconductors, materials, well, you get exactly the same thing. You get this. Here you have electric flux, which is that one. That one and that one are equivalent, okay? Because D is proportional to E, that in turn is proportional to J. It's all electricity. You get the Gauss magnetic law, and then you get a new heat. Since you are in a conductor, you get a very important effect, which is the Joule effect. While these terms are very small, the Biot terms are very small and only appear in special situations, Joule effect produces a huge amount of heat, and it has to, for conductors or semiconductors, has to be taken into account. You start for semiconductors, thermoelectrics, you get more couplings. J is equal to gamma conductivity multiplied by E, which is Ohm's law, that's all. But then you get couplings, which is Seebeck and Peltier. Okay. These are the constitutive equations. Again, this one and this one are exactly the same. This one and this one here. Let me find. And this one here are exactly the same, but they are written in a different with a different notation. Here you have that sigma is the derivative of the potential. Oh, this is of the functional. This is why we needed a potential, because by deriving the potential with respect to the primary, to the which variables, let's check. With respect to the extensive variables, is when you get your final constitutive equations. Here we don't write delta T. Delta T is the increment of temperature. We write that way because from thermoelasticity, we finish with this term, logarithm of T divided by something, okay? If you have an increment here, the increment of one, the logarithm of one is not very well defined. Okay, so we have here all of the extensive variables that are found by the derivative of the functional with respect to the extensive variables. Okay, in a box set are the direct couplings, and everything else is, excuse me. Yes, and the ones that are not box set are the couplings, lots of couplings. And here you have for the semiconductor materials. The mathematics are slightly different. The electricity has to be treated different. We don't have time to go to all details, but notice that here we have, this is the symmetric part of the Maxwell tensor, okay? And this is the non-symmetric part of the Maxwell tensor. Okay, well, just to expand the constitutive equations for piezoelectrics that only couple mechanics and electricity, and they are very important, piezoelectrics, you finish with this expression. This is the 3D expression. As I mentioned before, for 2D, you neglect, you consider that sigma 3, sigma 4, and sigma 5 is equal to 0. And then you start deleting rows and columns. Okay, and the same one for D. You neglect D2. D2 is neglected. Okay, and this is for piezomagnetics. For piezomagnetics, instead of having the piezoelectric couplings, again, something that you need to measure. Somebody has to go to the lab and measure that. So far, nobody has invented anything that can completely substitute going to the lab and measure. And here you have the piezomagnetic. Notice that the piezoelectric coupling, you finish with a matrix that is not symmetric, it's anti-symmetric. Here you have minus E13, and you have here plus E13. That's not a big problem. That's not a big problem because the matrix is still very well posed, and it can be inverted. Numerically, it can be inverted without any trouble. Well, okay. Boundary conditions. Well, you have to specify voltage somewhere. You have to specify temperature somewhere, and you have to fix the solid. You cannot leave the solid free in the space. You have to fix with the boundary conditions. Okay, now let's talk briefly, because we don't have much time left, about active materials. Active materials, which ones are? Well, Peltier cells, for instance, thermoelectrics, and they are making them very, very small. And they are making them not only from classical materials, but also from polymers. They are doing very interesting things. They put these things into cloths, okay? And yes, with the movement of a person, they can generate enough energy, for instance, to have communications, or for instance, to have heating. Just from the movement of a person, they can generate some heating. Some researchers in Israel have even realized that the yellow and black of wasps, of insects, have thermoelectric properties that allow them to move during the day in the desert. Okay, they auto-refrigerate themselves because in their cuticula, this is called cuticula, they can produce cooling from the heat of the sun. Okay, every cause has an effect. This is what we have called before intensive and extensive variables. And as I mentioned several times, active materials are able to couple. Piezoelectricity, magnetostriction, pyroelectricity, thermoelectricity. there are many special materials, and there are more and more that you can use the formulation I presented for to study them. Well, effect, you have first order, second orders, etc. And here you, on the top, then you have to go to more thermodynamics. You have that one we have seen before. That's a little different, but this is good only for solids. When you go to flows, and flows, for instance, is electric flux, magnetic flux, etc., you have to use non-equilibrium thermodynamics. What is going to change is the way you express the entropy. That's what was going to change, and that's what's going to change also your final element. Nothing to say about the box up, but something to say about the box down. Notice that here you have electric field, while here you have a gradient of V. We know that both are equivalent, but the extensive, instead of the extensive effects, now you will have fluxes. What are fluxes? Well, electric flux for sure is an electric flux. Thermal flux for sure is a flux. But you have polarization rate, magnetization rate, and strain rate. This is the way you can introduce things like, for instance, plasticity. Plasticity is this thing. Plasticity is the rate of the deformation. Okay. Here you have a representation of the other. You have a region of linear, non-linear, reversible, non-reversible. If you turn that figure 90 degrees, is when you finish with the plasticity. For those of you who work in mechanics, that's very common. That's very common. Okay. You know that in plasticity, when you surpass certain level of stress driving force, the intensive cause is what I mean. Then you get some extensive effect, which is remaining deformation. Okay, so something that, for people working on solids are very common. As the general picture is given here. Okay, well, couplings. Well, this is the Heckman diagram. This is what I mentioned before. All of these 4, 9, 7, 10, etc. are couplings, are defined here, and are the elastic tensor. It's a graphic way of expressing the matrix, the big constitutive matrix from before. Same thing from non-equilibrium dynamics. You have voltage, you have temperature, fluxes, both of them fluxes. Notice that you can have concentration also, like chemical reactions. Chemical reactions can be put here. You can put a porosity, a seepage, these things that people in civil engineering use a lot. And you can put many plasmas. You can put plasmas here, although plasmas are liquid. So with plasmas, you will have to go to the Cauchy tensor and do some things with it. You will have to divide the Cauchy tensor into a deviatoric part and another part. The deviatoric part is 0, and the spherical part of the sigma is the pressure. But you have to do things. But in this context, you can put many fields of physics. Magnetics, well, you could have magnetics here, why not? You could have magnetic flux here, but it gets very complicated. So there are some alternative formulations in which you put the magnetic field out. And you have to consider the galvanomagnetic and thermomagnetic couplings. What you do is that you have this alpha coefficient. I mentioned that when I was talking about Peltier. Let me see if I can recover that. It's coming. Here it is. Civic alpha. This is the coupling between electricity and heat. Only in a few materials. Not all materials are the thermoelectrics. Only in a few materials. Well, so instead of having a scalar like that one, you finish with a tensor. And let's see what the tensor is. This is not done by us. This has been done from the physicists since the middle of the 20th century. Okay, so instead of having a single coefficient, coupling coefficient, you create a tensor. And in this tensor, look, there is the magnetic flux. And also there is a new coefficient called Nernst. Okay, and for conductivity, rho is the inverse of gamma, which is the conductivity. Then you have this anti-symmetric tensor with this coefficient R, which is called Hall. Hall is very famous, no? And finally, for thermal conductivity, you construct this new anti-symmetric tensor with this, again, new coefficient M, which is called the Ricci-Leduc. All of these three are magnetic effects. Hall effect is very important. Hall effect is extremely important. It has to be studied in semiconductors. Electronic circuits are getting so small, so reduced, so miniaturized that now the magnetic field of one conductor with respect to the other, let's say the magnetic field created with one conductor is influencing the other because the distance is not anymore in millimeters. Now the distance is in microns. Okay. Okay, finite element. We are going to finish very quickly. Everything is ready. Everything is ready. Our degrees of freedom are the 6 I mentioned before. 3 displacements, 1 voltage, 1 magnetic potential, 1 temperature. The residuals, the finite elements are going to be nonlinear. Okay, so you have to define a residual, which is the derivative of the equations we have used before, of the balance equations. So it's ready. And you will finish with a stiffness matrix, which is the derivative of the residual with respect to the degrees of freedom, with this capacity matrix. It's called capacity coming from heat, on the heat equation. But look, is the residual with respect to the first derivative is not only a heat capacity, it's also with respect to the degrees of freedom mechanics, with respect to the magnetic and electric degrees of freedom, and you have a mass matrix, which is the residual with respect to the second derivative of all of those. Some of these terms are negligible, some others are not. Okay, you have to express all of your degrees of freedom with, say, functions. This is basic finite element formulation, including the space. The space is also discretized in say, functions. And interesting, epsilon, E, and H, which are the extensive variables, now are going to be, well, you only have to, for epsilon, you only have to be that one and derive with respect to space, this Nabla symmetry. And you finish with a new matrix, which we call B. B is not magnetic. B is derivative finite element matrix, symmetric. And you will have several of those. These are the shape. That comes from mechanics. That's for the potential fields, thermal, magnetic, and electric. And that's in the case you conserve some of the cross products. These are the residuals. I only take the equilibrium equations before, apply the divergence theorem, and this is what I get. You also have seen something before in classes before about the applications of the divergence theorem. Notice something important. Here, when you apply the divergence theorem, you finish with a flux integral. an integral that goes through the boundary. It's not the same, the boundary for mechanics than the boundary for electric and so on. They can be different, important issue, okay? For instance, you have a dominion, and you can fix this dominion, which is the mechanical gamma. But the voltage could be fixed in some other points. That's the electric boundary and so on. You have to take into account also the Biot terms. So, well, once you have cleared the formulations, to put into finite elements, if you have some experience, is more or less automatic. Then you have to run cases and see if it works or not, because not always it works. You have to fix things. But anyway, that's the idea. Well, and just to finish it, because we don't have more time, Peltier cells, look, well, we did all of this in the past, all of this formulation applied to finite elements. We coded in FIP, which is a program from the University of California at Berkeley. This is a Peltier cell. This is the one I mentioned that converts electricity into cooling, and it has this form. We are not going to details. But anyway, once you have, the thermoelectric elements really are these central rectangles here. You connect them by copper, and you recover that with alumina, which is a complete dielectric. It can transmit heat, but it cannot transmit electricity. And this is the type of results you finish. See, with the previous formulation and the finite element program FIP, coding a special element, you have to code the special element, because this is a research code. It's not like ANSYS that have some things on it. Then you get the distribution of voltage, linear. You get the distribution of temperature. Interesting. Look, you have higher temperature at the center. Do you know why is that? Because of the Joule effect. Okay, Joule effect is volumetric. You get fluxes, electric fluxes. You get heat fluxes. You get everything you want. Okay, even you can apply magnetic field. Because we have the magnetism in the formulation. Somebody discovered that if you apply a magnetic field to thermoelectrics, you increase the efficiency, and it is true. It is true. People have done experiments, and it is true. Since the magnetic field has to close, it makes some kind of circular lines. Well, so somebody else discovered also that you have to incline. You have to incline the thermoelements so that they are more efficient. And anyway, you can finish with many more applications. Okay, so that's all. I hope you retain the important concepts. Forget about the mathematics. You can work it out in the future if you want from the publications or from the books, but try to retain the concepts. Any question? Hello, are you there? Let's see. Samir, are you there now? Samir. Biljana, are you there? I don't know if those are people. I assume those are the participants, no?
Professor, may I have a question?
Sure. Who are you?
Yeah. So I think we didn't receive the slide, right?
The slides. I gave the slides to Emina. She has them. She has them already. I assume she will distribute them.
I had one, but I think that is in the old version. It's not exactly the same, the current one.
I cannot understand you very well. There is some echo. So try to speak it slowly.
Okay. So I have one version, but it is not updated. this is, I think, the current really updated one. Okay, by the way, I will contact Emina for this slide.
Yeah, the version you have is probably from Sarajevo.
Yes, that's right.
It's similar, but I have polished it. There were some mistakes there, some small mistakes, but well, when you don't know what's going on, they are important. Okay. If you have questions, you can always, if you are at the conference, you can ask me, or if not, send me an email. Okay.
Yes, thank you, Professor.
Okay, thank you very much for your attention. And I guess we will go to the next talk. Bye.